These expressions help design modern technology.
Oh, really? How?
You'll see. But first, let's understand what they mean visually.
Hmm.
Okay, we have already seen that a complex exponential represents the idea of a counterclockwise rotation by an angle theta from the real line.
Why do you consider only counterclockwise rotations?
That's just the usual convention, but nothing can stop us from moving in a clockwise direction. Now, there must be a way to indicate the direction of rotation in this expression, right? Can you guess what that modification would be? It is e power minus j theta. This can be easily obtained using the rectangular coordinates of these two complex exponentials. So e power j theta and e power minus j theta have the same real part and their imaginary part varies only in sign. These complex exponentials are called complex conjugates. Now coming back to the fact that e power j theta represents a vector of unit magnitude, we can construct any complex number of arbitrary magnitude by appropriately scaling it. This representation uses the polar coordinate system. Next up, we have addition.
What's the point of knowing how to add complex numbers?
Okay, how about this? The equipment that we connect to the AC power supply, like lighting, air conditioners, heaters, motors, and so on, can be represented by complex numbers.
What? My refrigerator is now a complex number? But why are complex numbers even able to represent the behavior of electrical equipment?
Great question. It's because of the way the elements of the equipment respond to the AC power supply. But we need to get a few more concepts straight to answer that question fully. So hold on, we'll address this in another episode, I promise.
Okay.
Let's say you've connected a bunch of equipment in series like this. The effect of all of them put together is given by the sum of these complex numbers.
Oh,
However, this is not how houses are actually wired, because if one equipment fails, the rest cannot operate because the circuit is broken. Houses are typically wired like this, so that even if an equipment fails, the others can continue to work. The effect of all of these equipment connected in parallel also depends on the sum of complex numbers. This way of modeling the electrical equipment helps to efficiently design, analyze, and stabilize the power system. So, what do you think of addition now?
interesting.
Now, coming back, we've already seen that we could add a bunch of complex numbers by first stacking them head to tail and then traveling along the path to reach the resultant. So, this is what addition looks like on the complex plane. Now, given that complex numbers have directions, how do I go from here to here?
Like this.
Yes, but how do I represent it mathematically?
Mm,
Okay, let's shift this vector to the origin to get a better idea. Now, to reach this point, we could first traverse through B and then through minus A, giving us B minus A. So, we could think of vector subtraction as the answer to the question, how do I get from this point on the complex plane to this other point? And if you calculate the magnitude of this vector, it gives you an idea of the distance between the 2 points.
and how do you calculate that?
Hold on, we'll get there. Let's say you want to multiply these two complex numbers on the unit circle. Think about it geometrically and tell me where the resultant is.
Uh,
It helps to interpret complex numbers as rotations.
So we first rotate by an angle theta and then by phi. That would give a total angle of theta plus phi. That's it. That's the answer.
Yep. I leave it to you to imagine what this would look like. Now, what if I want to rotate this vector by an angle theta and then bring it back by an angle phi?
Okay. This is r e power j theta. Now the direction is reversed. So multiply by e power minus j phi. Hey, it's division.
Exactly. So, multiplication and division can also be seen as rotations on the complex plane.
Nice. It's like z is being carried away to new locations depending on what multiplies it.
A great observation. This carry analogy is actually pivotal in the development of radio broadcasting systems, where speech and audio are carried from the transmission station to the receivers.
What?
Yep. The technology of amplitude modulation is based on this carry interpretation of multiplication.
Oh,
Now, coming back to your question, how would we represent this magnitude or length in terms of the complex number c?
put two vertical lines on either side of c?
Very funny. Come on.
Okay, we have this, let's say. But I want only r. So I have to negate the effect of e power j theta by rotating it back by minus theta. But you want everything with c. Oh, I could consider the complex conjugate. Oh yeah, multiplying the complex conjugates would give me the square of the length of the complex number. Nice.
Exactly. So we make an important note here that complex exponentials can come together to give us a real number. Now I leave you with a question. Do you think we can represent real quantities like sine theta and cos theta using complex exponentials? Think about it. And we'll meet you in the next one.